Okay, so we've talked about how energy is 1/2 mv squared, and the change in energy is something we call work, and then work is force times distance. And this all works very well in one dimension. So we want to try to extend this out to 2 and 3 dimensions and see how can we apply these concepts when we've got a 2-dimensional situation, let's say. And then you'll see the 3-dimensional is basically the same. So where we got all this from, you'll recall, is our old friend, actually I'm going to write it like this, v final squared, or v1 squared, equals v0 squared plus 2a delta x. And in the one-dimensional case, this was acceleration in the x direction times delta x, right? So we had something moving along the x-axis, some distance delta x. Its acceleration was, so let's say it moved distance delta x, and its acceleration was a sub x, and you could find its initial velocity in the x direction. Well, you could find, if you've given its initial velocity in the x direction, you could find its initial velocity, or its final velocity in the x direction, vice versa. So this all applies along the x-axis. The x component of velocity after, before, acceleration in the x direction, and the distance, or the change in your x position. So that's all well and good. And we were able to just multiply this by 1/2 m and basically get out, your energy work relationship. So to extend this to a 2-dimensional case, what we want to do is we want to take, instead of the x direction, we want to take the y direction equation as well. I'm just going to write this below the x1. And it's, of course, the same. You just change all the x's to y. So acceleration in the y direction. And that's all good. So now we've got this thing can also be moving in y and have some acceleration. That's all. I don't know. That's all good. Whatever. It's moving around in there. And so what we can do here is a kind of little trick where we basically take these two equations and we add them up. So we're going to take this equation and add this equation to it and see what we get out. I think we'll be a little surprised, but or I won't be surprised because I've done this before, obviously. You might be surprised, although maybe not if you've been paying attention up till now. But we have v1x squared plus v1y squared. This is the x and y components of the final velocity, v0x squared plus v0y squared. So that's these two terms adding up here. And that's going to equal 2. And I'm going to collect everything in the 2 here. And we're going to say ax delta x plus ay delta y. And so now we've got this nice equation here, which sort of, oh, well, I'm sorry, this is, it actually should be a plus sign. Let's see if I can erase this one. Yes, I can. So, plus. There we go. Okay, so what's interesting now is if we look at this term here, this is the x component of velocity squared plus the y component of velocity squared. And you'll recall, I think, that if you have some velocity like that, then you've got, let's say you've got an x and y axis like that, okay? Then this is your y component of this velocity v, and this is your x component of this velocity v. And the length of this vector v is just, you just use the Pythagorean theorem to find this out. So really, this here is just the square of the length of this velocity v, or the speed. Square the speed, the final speed v. So really, this is just v1 squared. This all here turns into v1 squared. And this here, as you might expect, then turns into v0 squared. So I'm going to continue this. Now, what does this thing here turn into? Well, so let's look at this. You've got an acceleration in the x direction, a component in the x direction, an acceleration in the y direction, and a change in position in the x and y. So what I'm going to ask you to consider here is, let's say we have I'll do this in red. Okay, So you've got an acceleration. Actually, let me draw it this way. So you have some acceleration here, and you break it into components just like we did with velocity. So same deal. We have a coordinate axis. There's a y, there's a x, and so you have this thing here. And so if you were to represent this in ij form, remember I is the unit vector in the x direction, j is the unit vector in the y direction. So a, this a vector, is ax times I hat plus ay times j hat. And then, so what else can we do here? Well, let's say we're I'm going to draw a little sort of a little fence here to keep this separate from our equation, even though we're talking about this thing here. Let's say this, we have this thing, and this is the position R1, and it's measured with respect to some origin or reference point or whatever. We don't really care. And this is R2. Actually, let me make this R0, and this will be R1. So this is its position at time 0, and this is its position at time 1, or initial and final. So this here, this vector here, is it's going to be R1 minus R0. Is this vector here, but we're just going to call that delta R. Okay, so you can imagine R1 is some position like x1, y1. So this is going to be x1 I hat. Well, I don't want to draw it there, but so if we do, say, let's see, R1 equals x1 I hat plus y1 j hat, and R0 equals x naught I hat plus y naught j hat, then you can see, I think, that delta R is just going to equal delta x times I hat plus delta y times j hat. It's just, this change of position vector, this displacement vector here, delta R, is just the change in x times I hat. So here's your delta x in the I hat direction, and then here's your delta y. So this is delta x and delta y. That's pretty easy to see. In fact, I probably should have skipped all this part, but whatever. So you get the idea there. So then what does this turn out to be? Well, this acceleration vector was ax I hat plus ay j hat, and the delta r vector was delta x I hat plus delta y j hat. And you can see, I think, maybe it's not immediately obvious, but when you think about it a little, this is just the dot product of this a vector with this delta r vector, right? Because you take the I hat here, and the I hat component is ax, and the I hat component here is delta x, multiply them together, there's that term. And you take the ay and the delta y, multiply them together, and there's that term. So what this ends up being, there we go, is 2 times the acceleration vector dotted with, I'm going to put parentheses just to be clear, but it should be pretty obvious, delta r. Okay? So this equation works down to be final speed squared equals initial speed squared plus 2 acceleration dot r. So now we're going to do our same trick from before, and we're going to multiply this all. We're going to take this entire equation here, okay, and we're going to multiply it by 1/2 m. And so what we get out of that, I'm going to do this in purple now, just to be changing colors, is this becomes 1/2 m, let me move that up a little, 1/2 m v1 squared equals 1/2 m v naught squared plus 1/2 m times this. Well, 1/2 cancels the 2, so it's just m a dot delta r. And so now, it should be pretty obvious to you at this point. This is just the final kinetic energy. This is the initial kinetic energy. So this is going to be EK1 equals EK0 plus, and then what's m times a vector? Ma is force. So this is just, remember this, F equals ma, Newton's second law. Okay, this is force dotted with delta r. which means, and so this term here. I mean, this is just our change in energy, right, over on this side. So this is going to be, if we bring the EK0 over, we can say change in kinetic energy. And this is for one object. We're going to extend this to multiple objects in a bit, but really, all this stuff where we have like delta EK equals work, this is just one object. Okay, for only one object. Later on, we'll get into multiple objects systems and how that works. But for now, one object equals, and this F dot delta R term is actually just work. So same equation here for one object. Circle this and say just for one object, and work equals force dot displacement. And this is also for constant force. So for a force that's not changing, this is work. Work is F dot delta R. And this is a very powerful result. And you'll see that it lets you make some problems that would be hard very easy. You're going to like this because once you understand how this works and you understand how to apply it, it's going to feel like cheating. I mean, literally, you're going to be able to solve problems that you would never dreamed you could solve by using this, and it's going to feel like you're cheating, but it works, and that's why this is such a powerful concept. So I'm going to get to those in just a second in the next video.